We've seen a few examples of sliding window technique in action by now. The first one we started with had a fixed window length. From there, we moved on to a variable window length, and then, in addition to variable window length, the usage of additional data structures. Before we move on to even tougher problems, now would be a good time to summarize and reflect on what we have seen so far. Let's begin by thinking about when exactly should you think about applying sliding window technique. A good signal to look out for is the usage of terms like subarray or substrings in the problem statement. The window slides, it does not skip, it doesn't break, it slides by shrinking and expanding, very much like a worm. So the technique would be irrelevant in problems dealing with subsequences where continuity isn't guaranteed. Keep an eye on words like subarrays or substrings. It's a solid hint that sliding window technique is a potential way to the solution. Another one is that these problems are usually interested in an optimal solution. That is, there is a notion of longest or shortest, minimum or maximum in the problem. Finally, you'll see most of these problems have a very obvious quadratic or exponential brute force solution, and you're looking for a linear one. Let's move our attention now to the general template that you can use to write a sliding window solution quickly. We'll maintain two pointers, rear and front, that will mark the ends of the current window. Expansion is done inside a while loop which goes from front equal to 0 to subarray length. Inside, we add the front element to our window, updating any additional data structures like a hash map that we might be maintaining. Next, we check if expansion led to any unsatisfied constraint. If it did, we use another while loop that runs as long as the constraint is unsatisfied. Inside, we increment rear and update any other data structure we might be maintaining. After this, we now have a window that satisfies given constraints, so we update the result according to the situation. And that's pretty much it. Most sliding window problems will use this general template. You can fill out the paths to quickly code a solution. Obviously, this template works for varying window length problems. Fixed window length problems are pretty straightforward. Finally, let's take a closer look at time complexity. Consider this movement of the window in some sliding window problem. Looking at it, it's not very obvious what the time complexity is going to be for such a traversal of the array. Let's take a look at the template we just discussed. Can you put an upper bound on the time complexity looking at the general template we have laid out here? The key observation is that front is always moving forward in every iteration. It never moves back or stays in place. Rear's movement is not very defined. It could stay in the same spot for some time, skip few indices forward, or just move forward consistently like front, but in any case, it's always behind or at the same spot as front. If you remove the shrink phase, that is the inner while loop, the time complexity is clearly linear. The inner while loop will take maximum time if rear goes through each of the array elements. It could happen if the window moves in alternating shrink expand fashion. Notice how rear is going through each array element here. It could also happen if the window first expands to array length and then shrinks one at a time. Again, rear is moving through each element. In both of these cases and in any other such possible case, the maximum overall time taken by the inner while loop is also linear. So the overall time complexity is going to remain linear if we only do constant time operations inside both outer and inner loops. That's it for this one. Thanks for watching.